In today's session, we're going to be looking at integration by parts. We're going to look at some challenging examples, especially for those who are targeting grade A star in their A-level summer exams. All right, so we're going to start off with the formula for integration by parts. So standard representation is as on the screen. We have the integral of u times v dash d with respect to x is equal to uv minus the integral of v times u dash with respect to x. So we're going to start off with the following example. So example 1, integral of sine x ln sine x. So the first couple of examples will be a single application of the integration by parts formula, and then the remaining examples will be a double application of the integration by parts formula. So in terms of standard presentation, we want to identify our u. In this case, the u will usually be the function that involves an ln. So u equal ln sine x, and then u dash is going to be the derivative of sine x is cos x, and we put that over the argument or the input sine x. V dash will be sine x, and the integral of sine x is going to be minus cos x. So we apply the formula at the top of the screen. One way to remember the formula is this way. So we're going to multiply the two things in the diagonal. So the integral is going to be equal to u times v. So that's going to be minus cos x times ln sine x. And then minus the integral of u dash v. So that will be minus cos x times cos x over sine x dx. So here, the minus times the minus will give us a plus, so we can simplify this. So we're going to have the integral is equal to minus cos x ln sine x, then plus the integral of cos square x over sine x dx. So what we can do here, we can rewrite cos square x using the identity that cos square plus sine square is equal to 1. So this can be reframed as cos x ln of sine x, and then plus now the integral of 1 minus sine square x over sine x dx. So let's tidy this up a little bit. So what we're going to do is we're going to use the following result, that if we have, we know that if we have a plus b over c, that this is equal to a over c plus b over c. So we're going to apply that now to the to 1 minus sine square x over sine x. So this is going to be minus cos x ln sine x, and then plus now the integral of 1 over sine x minus sine square x over sine x. Multiple terms, we'll put that in brackets. We know that 1 over sine x is cosec x, so this is minus cos x ln sine x plus the integral of cosec x, and then sine square x over sine x, that gives us sine x dx. Now we can simplify this. So this is minus cos x ln sine x. Now what we can do is, if you're not sure of the integral of cosec x, you can go to the formula booklet. So if you're doing Edexcel, you can check for the standard integrals for Edexcel. All right, so let's have a look at that. So here we have the standard integral for cosec x being -1, cosec kx being -1 over k ln cosec kx plus cot kx. So we know that in this case k is going to be equal to 1. So we apply that. All right. So this will be plus, or rather minus. So minus ln cosec x plus cot x. And then when we integrate minus sin x, we get cos x. And then plus c. So that will be the final answer. Now, reflecting on what we have here, notice that I played a little bit fast and loose with notation. So ideally, when you take the natural log of sin x, it should be in absolute bars. So here, this should really be absolute bar here, and then here. So throughout, we should have absolute bar. But the examiner won't penalize you if you choose to use rounded bracket rather than absolute bars. All right, so just be aware of that. It may be useful to include the absolute bars, especially if you have integrals, and sometimes the examiner may be cheeky and give you an integral where the argument so what you're taking the ln of is a negative value, and it is for us to remember that it is the ln of the absolute value of the input, and so in those special cases it might be useful to keep the absolute bars. Okay, so we'll pause here and then we'll move on to our next example shortly.